Okay, let's take a first look at a special case of the Runge-Kutta method called Hume's method or Hoyne's method. I'm not sure how you pronounce it. This is the generic Runge-Kutta formula. yi plus 1 is equal to this, where k1 and k2 are defined below. And remember, we have four unknown parameters, a1, a2, p1, and qii. Well, Hoyne's method simply says, make a sub 2 equal to 1/2. Simple as that. So, this formula we saw earlier, a1 plus a2 equals 1, means that a1 is equal to 1/2. So there's two of our parameters. And then if a2 times p1 is equal to 1/2, which we saw earlier, that means p1 is equal to 1. And likewise, a2 qii is 1/2. That means that qii is equal to 1. So Hume's method uses these four values for the unknowns up here. And we end up with this. yi plus 1 is yi plus 1/2 of k1 plus 1/2 of k2 times h. K1 is just f of xi yi, like used in Euler's method. K2 is f of xi plus h, a time in the future, and an estimate for a y in the future. So we're taking, in Hume's method, simply the average, 1/2 and 1/2, adding these together, of k1 and k2, the average of the two slopes, the current slope and the averaging that with the slope of a point approximately where we're headed. All right, let's do an example of using Hoyne's method. Same differential equation we've seen before. Dy dx is 3e to the negative x minus 0.4y. And the initial value says, I'm going to think of x as being time, so I'm going to say at time 0, y is 5. Really, when x is 0, y is 5. Find y at time 3 using a step size h of 1/2. So how many steps will that be? Well, the first step will go from 0 to 1/2, and then the second step will go from 1/2 to 3. So 2 steps. This is our reminder. This is Hoyne's formula. So it's here along with what k1 and k2 are equal to. And let's see. Am I missing? Nope. That is correct. Okay. So when I is equal to 0, we know the initial value. x0 is 0 and y0 is 5. I see. That's just the initial condition given to us. Now, though, we're going to use this formula. So when I is a 0, now we're computing y1. All right, well, before we do that, let's compute both of the k values. And let's make a reminder here. This is f of xy. dy dx is f of xy. So k1 is f of that, which is f of 0, 5. So we have to plug in 0, 5 into that formula. And we get 3e to the negative 0 minus 0.4 times 5. So that's 3 to the 1. That's 3. 3 minus 2 just gives us a 1. So k1 equals 1. All right, k2. It's a little longer. k2 is f of x naught plus h, comma, y naught plus h, k1h. Now notice you have to compute k1 and k2 in that order because k2 uses k1 right here, so you need to know what k1 is. This k1 is going to become a 1. So this is equal to f of 0 plus 1.5, and y0 was a 5, so 5 plus 1 times h, which is 1.5. 1 times 1.5. That's equal to f of 1.5, comma, 5 plus 1.5 is 6.5. Okay, and if we plug this into f, we get 3e to the negative 1.5 minus 0.4 times 6.5. And this is about negative 1.9306. That's K2. So finally, I'm going to squeeze it down here at the bottom. Plugging into this formula, we get y1 equals y0, which is 5, plus 1/2 of k1, which is 1/2 of 1, plus 1/2 of negative 1.9306, that's k1, and all of that, let's see, am I missing an h? I am missing an h right here. That h I was missing out of the formula. So now I need to multiply that by h, which is 1.5. So y1 is equal to 4.302. y1 is equal to, and it's approximately equal to 4.302. Maybe I'll make it approximately equal to. And I'll also say on this side, y1 is actually y at time 1.5, because if you think of y0, y1, and y2, that's y at time 0, it's y at time 1.5, and then it's y at time 3. So we're halfway there. So let me, one more step to go. I equals 1. Okay, so I equals 1. What are we starting off with? x1 is equal to 1.5. y1 is equal to what we just computed, 4.302. And now let's compute k1. K1 is f of x1, y1, which is f of 1.5, comma 4.302. And if we plug this into f right here, we get 3e to the negative 1.5 minus 0.4 times 4.302. And that's equal to negative 1.0519. That's K1. Now we go to K2. K2 is a little longer formula. It is f of x1 plus h, y1 plus k1 h. And that gives us f of, I'm going to skip a little bit of arithmetic. We would just take x1 is this number, h is 1.5. It would give us f of 3, comma 2.726, which is negative 0.9406. That's K2. Negative 0.9406. So we get that y2 is equal to y1 plus, I'll go ahead and write it down again, 1/2 k1 plus 1/2 k2 times h. That's equal to 4.302. That was our y1 we computed, plus 1/2 of k1, which was, k1, negative 1.0519, plus 1/2 negative 0.9406, and close parentheses, times 1.5, which is h. And that gives us that y2, I should probably be using approximately equals, but just assume we're rounding out to about 3 decimal places, 2.808. Well, y0, y1, y2. y2 represents y at time 3. That's 2 time steps away from 0. So this is our approximation for y of 3. Let's just make a note that the exact value of y of 3 is 2.763, giving us an absolute relative error and I make that little subscript of t just because this is based on truth. It's not based upon the 2 previous iterations. We know what the exact value is. It is 2.763 minus 2.808 all over 2.763. And that written as a percent is 1.63%. Relative error. So that's really excellent compared to the first order method that we did with the same differential equation using Euler's method.